from what I've heard, I'm also scared.
I don't know.
We'll see though. We'll see, and my goal will be to curb as necessary, because if the class as a whole performs poorly on something, I always try to take responsibility for that, because it's not like everyone in here is conspiring against me to fail the class.
Yeah. No, we don't. We're actually, it's so effortless, we don't even have to try.
Although with this particular class, I am less sure than I ever have been historically that is not happening.
It's a good call. It's not like we talked about all family.
Right, exactly.
Is this something difficult thing, so it's reaching this back.
David's already built an email bit.
So, to recap kind of where we were at the end of the last class, we were talking about propositional logic agents and how to represent some propositional logic within the environment. So we had introduced the idea, we talked about how to represent things, we talked about some different axioms that we could use, like framed axioms, effect axioms, and I'll try to quickly go over those, kind of solidify where we were before we move forward, to give you kind of a bird's eye or top-down view of where we're going with this. A lot is not done with propositional logic themselves, but it's used for predicate logic agents. So as we discuss this, we're gonna talk about a lot of what's wrong or inefficient with the use of propositional logic agents, and then take a lot of that knowledge and apply it to predicate logic agents to say, what can we actually do with this in a way that actually, it doesn't require you to insert 10,000 assertions, tells into a knowledge base before you can do anything. So effect axioms, we talked about how something like we could utilize the current position at a current time step. So this said the location at when we're at 1, 1 at time 0, and we're facing east at time 0, and we choose the action to move forward at time 0. That implies that both we know that we have moved from location 1, 1 to 1, 2, which tells us two things that aren't necessarily inherent in the logic themselves. We now are in 2, 1, location 2, 1 at time step 1, and we're no longer in 1, 1. Note that nowhere in this logic does it say things like you can't be two places at once. So if you don't specify that very end, and we're not at the location 1, 1 at time step 1, you might have an ask of your knowledge base eventually that says, am I in 1, 1? It's like, yeah, you never left, you just duplicated yourself as you move forward. And so you have to account for that, because there is no, the way that you might think logically, the machine, of course, as you've experienced every time you write a program, the machine doesn't interpret anything that you don't tell it to, even if it's obvious to you. But being able to do this helps us a ton. You can think of the difficulty here as the dimensionality problem. As we input, there are associated inputs for all of the percepts for this, for our location, there's so many dimensions to this that when we make an associated change, we're moving in all of those dimensions. So anything we can do to shave a dimension off of that is useful. It removes one component of an exponential search space. So we talked about all of this. We talked about how none of this solved the arrow issue, and we needed a frame axiom to be able to handle the arrow issue. Something that says that unless you shot in the last time step, you're still going to have the arrow. Once you have shot, you no longer have the arrow. So we had the concept of a framed axiom that we could somehow factor out the value of the time, some way of saying, all right, if we move forward and we had the arrow, then there's no way that we don't have the arrow in the next time step, because you can't move forward and shoot at the same time. And unless we specify something like this, maybe that's possible. There's nothing that says you can only do one action in a particular time step unless you embed that into the model. Similarly, if you choose to move forward and the Wumpus was alive at time t, the Wumpus will still be alive at time t plus 1. There's no way for the Wumpus to die unless it is hit by an arrow. If you didn't fire that arrow in that time step, it will continue to be the same alive or dead that it was in the last time step. So we can add these kinds of axioms as well, and now we don't have to worry about the associated logic of querying, is the wumpus alive? We know that now whenever we take the forward action, that we don't need to update the arrow or update the wumpus, that this logic will do it for us. It's now embedded in the representation, the knowledge representation of the domain. So instead of exhaustively listing everything, if we think of the world in terms of our effect axioms, our frame axioms, then this allows you to shave off some of those dimensions, save some time and space, which is performance. And that, at the end of the day, performance is everything. Let's see. We talked about fluence. So this was a general version of a fluent, and then we gave a specific example, something like, if we have the arrow at time t+1, it bidirectionally implies that we had the arrow at time t and we did not choose to shoot at time t. Both of those have to be true if we still have the arrow. As soon as we shot the arrow, we wouldn't have the arrow. So we can tell two pieces of information from the fact that we currently have the arrow. That is something about the last action and something about the state of the last world. So that's a way of storing history without actually storing the history. The history will propagate of the arrow forward in time now. We only have to worry about that changing when we shoot. And note that this will also tell us that the agent will no longer know that it has the arrow. It'll be unknown. It won't be able to verify has arrow at a particular time, because the time step before, when you choose to shoot, this fluent will not be true. Questions on that? Does that make sense logically? Then we figured out how to update the location as well. We unfortunately have to do this for every single location in a propositional universe, which we will find a way to get out of when we talk about predicate logic. But for now, if you're in location 1,1 at time t+1, then we were either in location 1,1 at time t, didn't move forward or bumped, or we were in location 1,2 and we were facing south and moved forward, or we were in location 2,1 and we're facing west and moved forward. Those are the only ways that you are in location 1,1 at the end of an action. You either were already there and you did something other than move forward, or you moved forward and got a bump, or you were in an adjacent cell and moved forward into that cell. Those are the only ways to arrive in 1,1 at a particular time step. So you can do that as, again, a fluent in a way that now you don't have to have rules for every action. You just now have rules based on every location. How do we arrive in a location versus an action oriented? How do we handle a particular action? I look to have lost most of you already. I see your confidence in me and my ability to inspire you, and I am further inspired. Yeah, it's true. We have done this slide before. I wanted to catch people back up. 2.5 hours, this is what people are gonna remember the least. Or maybe that's not true because it was right before we left. People are like watching the clock tick down and they pay a little bit more attention, who knows? Yeah, we talked about cells being safe. How do we determine that? The only ways for cells to not be safe are either if there is no pit in an adjacent cell, we know that it's safe. Or there is no wumpus in an associated cell and that wumpus still has to be alive. So that helps. We talked about things that can go wrong that our model is not handling, like the agent tripping and falling, being carried away by bats, having a heart attack, something ridiculous. But we said that we need to have some kind of probabilistic threshold for what is likely to happen versus not likely to happen. If it's especially likely, then maybe we want to handle it in the model. And if it's not likely to happen, then maybe that's not something we want to incorporate into the model. Or maybe a more cyber approach to this would be, how important is the unlikely event? Is it a catastrophic failure of the system? If even though it's unlikely, it causes data to leak or shows that there's been some kind of breach. Yeah,
It's why a lot of businesses have disaster recovery plans, things like earthquakes or floods.
Yeah,
You know, hurricanes.
it's not likely, but when it does happen, it's very expensive. Or, yeah, so it's not just necessarily a probability threshold, but maybe you include an extra dimension to the probability threshold of how likely is it times the effect of when it does happen. How prepared should we be for that? And that determines what's going to be added to the knowledge base, what's going to be used as part of the model. Is basically just what's important. And there are kind of two dimensions to that: the monetary cost of what happens when it goes wrong and how likely is it. So I see this as being related to that. All right, let's combine this into making a logical inference agent. This is where we actually stopped last time. So what does an agent that actually does this look like? If you were going to implement this and say, great, let's actually create an agent that's capable of understanding a domain and being able to intelligently choose actions within that domain based on the structure of the problem. Like you can imagine taking this Wumpus world and overlaying it onto really any cyber problem and saying the associated actions that the agent can do are the associated actions of the system. The associated responses from that system could be information that you gather from data logs or from activity monitoring. Then you take that information that feeds into a system that allows you to make an intelligent decision about how should I handle the current state of the system based on that data feedback, the percepts of this agent. So this agent's ability to understand the world around it is very much like an agent's ability in a cyber environment to perceive the safety of the network from the associated inputs. So I feel like they map onto each other well. Again, we just have to kind of draw the connection there. This is obviously a toy simplistic example for reasons, but this is in general what in pseudocode this would look like. Let's just zoom in on that and take a quick look at. I'll explain this in a little bit more detail as we do it. So what are we taking in as input? We take in the percept list. So something that is all of the data that we know from the current state. So in the Wumpus world environment, it's just, do we perceive a stench in one of the adjacent cells? Do we perceive a breeze in one of the adjacent cells? Do we notice a glitter? Did we experience a bump from moving forward and hitting a wall? Or did we hear the scream of a Wumpus dying? All of that information is all of the data we can gather about the current state. The goal of the output at the very end of this is return an action of some kind that says, what should we do given the parsing of these percepts and my knowledge of this environment? So what exists in storage as a structure is just this persistent knowledge base. This is going to be everything that we can do. This is our logical representation of the domain that we are in. And the ability to parse that is what we want to do here, giving an associated plan of action for given conditional states of the world, how do we determine which action to do? And in the Wumpus world, it's nice and simple as opposed to the real world where everything is complicated. So the first thing we should do is come up with a list of priorities. If we see the glitter, that becomes the single most important thing we can do. Why worry about anything adjacent to us being safe if we can grab the gold? We know we pathed here via some safe path anyway. We got here without falling into a pit, so we can get out of here safely. If we see the gold, grab the gold and get out. That becomes the top priority. If we don't see the gold, then we need to make some kind of intelligent decision based on a plan. So now we ask the question, is there an ongoing plan? Are we in the middle of trying to get out after having seen the goal? In which case we would want to query the plan and say, are we in the middle of pathing somewhere? If so, what is the next step of that path? If you are pathing to some cell that you have proven to be safe, it's adjacent to this cell and we know that it's safe, you can make a plan to get there. Maybe it's something that's adjacent that's not adjacent, it's not near you and you want to path to that. We can now create a plan to path from the current location to a location that's going to give us some more information about the state of the world. Maybe it even has the gold in it. So we check for a plan. We're going to plan the route to some unvisited and safe cell if we don't see the gold. If the plan is empty at that point, then we can figure out, all right, if getting past this point, if the plan is empty, then there is no guaranteed safe cell anywhere in the Wumpus world. There's nowhere that we can go explore that isn't somewhat likely to have a pit in it or a Wumpus in it. So at that point, we should figure out, do we have the arrow still? And do we know where the Wumpus is? Or do we have a guess as to where the Wumpus is? We can then make a plan to shoot the Wumpus. That would give us some more information. If there was an unsafe cell that we knew was unsafe because the Wumpus was on top of that cell, then when we fire that arrow, great, we can go explore that, and maybe the Wumpus was on top of the gold, like a good dragon. I'm just imagining Smog now in Wumpus form. What have you done to me? So that's the next priority, would be to, all right, if we can't do anything, can we create a situation where we can do something? Shoot the Wumpus, explore that cell. Then, assuming the plan is still empty past that point, know that these are not else ifs, they're just ifs, because this might create a plan. So going and shooting the Wumpus becomes a plan, so then if the next plan is empty, then we don't do what is embedded in that if statement. If the plan is empty at that point, then we have to take some kind of risk. And at least for this stupid agent, we're going to just choose randomly, I guess. We're going to go take a risk. We're going to figure out, okay, plan a route to some unsafe cell. If the plan is empty at that point, which means that we still don't have the gold, then we will plan a route out, which means it's likely that the gold was behind some kind of it was inaccessible. We couldn't do anything about it. So then we will add, after all of this, we will tell the knowledge base to figure out which action to do from that. Note that none of this has anything to do with figuring out which action to take from there. It's about creating the plan. Then you tell the knowledge base, here's the plan, tell me which action is the first thing that I should do given that plan. And it will return a list of actions of how to make that happen. And that's going to happen via propositional inference on the information in the knowledge base. So we can see that the plan route itself just then returns that list via a search. How do we do that? So, and we can, for that, we can use any search algorithm, any global search that we've already talked about. So you could use breadth first search or iterative deepening or literally any global search to return an associated path that guarantees safety from here to the goal that becomes 1-1 where you can climb out of the cave and escape the system. In a bit more detail, initially we contain axioms that don't depend on time, that's useful. And then every time we move forward in time, we just add a new percept sequence. So this new list of percepts to the knowledge base, along with any axioms for that particular time step that depend on time. And this way we don't have to do something like have all of the time step up to length 20. And then if we hit time step 20, we fail. We just on the fly say everything that depends on time, generate all of the new things that depend on time t+1 given our current state, tell those to the knowledge base, use that to determine what we do, return an action. Loop that process over and over until now we have a way of intelligently making action selections. We can use propositional inference. So just logic now to determine which squares are safe and have or have not been visited. So that just becomes the inference that's a part of this system. And then we have the action priority. So this just defines the action priority that's already embedded in the code that we talked about. If we use the glitter, grab the gold, plan the path to the exit. You can use any global search, including A star, as soon as we have the heuristic, which works because we have row column pairs, so we can use the associated heuristic from A star to minimize the associated cost of getting out. So A star actually will be an improvement over dumb global searches like breadth-first search. Yeah, the rest of it I've kind of already talked about. One thing to note as an issue with this is that as time elapses, we end up with more and more and more information in our knowledge base because we're adding more and more information about every new time step. And as we have explored more of the world, we continue to add more information from the knowledge base, and inference becomes harder and harder when we have more pieces of information to possibly bounce off. If I want to say, let's play Where's Waldo, and there are 2 people on the page. Where's Waldo is a really easy, it's really easy. Which one of these 2 people is Waldo? If you have Where's Waldo with 10 million people on the page, it's much more difficult because you have to ask that question and try to use additional information. So as there becomes more and more information in the knowledge base, you start playing more of a Where's Waldo with the decision of how to return the correct action, and it starts to take more and more time to inference the correct choice to make. That becomes something that we have to consider. The best thing to do is to give time the good old middle finger and try to remove it from the system completely. And if the way to do this is just caching. If you're able to take the results of inference and say, in this situation, we did this, then it stops becoming dependent on a particular time step. It doesn't matter if you're in exactly the same situation. Let's say we're in cell 2-1 at time step 7 versus in step 2-1 at time step 2. The inference based on the percept sequence that you're getting in the state of the world is going to be the same regardless of time step. It's actually independent of the actual time step that you aren't there. So if you cached the decision that you made at one point, then you would be able to look that up without having to re-inference or re-add a bunch of propositional statements that depend on time step 2 and then reinsert those exact same issues when time step 7 occurs. So cache the results becomes kind of like a dynamic programming kind of problem. And this allows us to now propagate that forward a bit. When we learn something from time step 2, we can now propagate it forward to time step 3 because it doesn't depend on the time step anymore because we cached the associated actions that we made. This doesn't necessarily make sense if what you do is based on a history of percepts, but because what we choose to do is just based, it adheres to the Markov property, and we'll talk about that in the next chapter that we covered. But what we do depends only on the current percepts that we experience right now. It doesn't rely on the history of percepts. So we don't have to do a lookup of what percepts did we get 5 time steps ago to make an intelligent decision about now. That's embedded in this state of the world. Where have we visited? Is the Wumpus alive or dead? We can determine that from the state of the world and logical inference. We don't need that percept history to do that. Remember that we can phrase things in terms of local search if we just select things as a belief state. So we could now allow for when we don't know the location of a pit, for instance. We know the pit is either here or there. We can now put this into a belief state that says we could either have a pit here or a pit there or a pit in both locations. And you can start to make actions that reduce the size of the belief state. if something that was adjacent to, let me actually draw this out so it makes a little bit more sense. If we have a world that, let's see, we start here and here, here we see breeze, and we want to answer questions about the associated neighboring, like, is there a pit here, here, or here? Something like this. The information that we could gain from this, like, is there a pit here? You could figure that out by visiting this location, even though it isn't necessarily safe. That would be better if there were a way around this. So maybe this isn't 1-1, but we allow safe. The fact that this is unvisited allows us now to go check this cell. If we don't get a breeze in this cell, we know that this cell is safe. So this would be what allows us to determine and deal with the ambiguity of this belief state of, is there a pit here? Is there a pit here? Is there a pit here? That allows us to craft and understand, if I go here, I can remove the ambiguity of whether there is a pit there. Or at least sometimes. There could be a pit here and a pit here. You're gonna get breeze in here, here and here anyway. But going here would tell you some information about there being a pit here, potentially. So that allows us to prioritize doing something like that. Does that make sense? I see intense enthusiasm. We're thrilled to be here and we know it. So we can use the concept of state estimation. As we get new information from new percepts, we can update our belief state. So something like when we explore an adjacent cell to what is potentially a pit, and we see that that does not have a breeze, that tells us that we can update our view of the belief state. Now we know there's not a pit there. And that collapses the belief state a little bit. We might go from 6 potential worlds in that belief state to 2 potential worlds or something like that. So we can collapse our belief state if we utilize some of what we talked about from local search in terms of what action set or what path can we create that would minimize the associated belief state of the world, given what we don't know about the world. I can see this being particularly useful in cyber. In real time, which data do we go analyze to try to figure out if something is wrong or not, if there has been a breach or not, if there is some kind of vulnerability or not? What do you do with your resources when you have a limited amount of time to try to figure that out?
Specifically in digital forensics, one of the first things that I do is go into the documents, the common things that, the common folders that people usually store things in. From there, I'll pick out like a timeline of things that are maybe a little weird or a little suspicious, and then I would just start going deeper from there.
Yeah, imagine now having an agent that does that for you, or that you program to prioritize an associated list of what is most likely to be able to identify the associated course of action. Is a course of action needed, yes or no? If you can design that agent, then all that has to happen is whenever that agent returns, it notifies someone who's responsible for administering the system, and then they go do the associated tasks that the AI tells you to do. Of course, that relies on, and we'll talk about monitoring that. Actually, we're developing a secure AI course that would tell you exactly how to ensure the health of that AI agent and that hasn't been tampered with. And it's not an outside agent that's telling you to go, just delete everything. That's the right call right now, trust me. So that's in development, but yeah, so the entire idea of talking about this is so that you can apply this to some kind of automation of a cyber domain to be able to make the informed sorts of, here's what the actions are, here's how to analyze a system, here's how that system can be logically determined from the domain of that system. So an example for that from state estimation looks something like this, where the WUMPUS is alive at time step 1, and the location that we're currently in is 2-1, and there's a breeze in 2-1, And there's either a pit in 3-1 or a pit in 2-2. So that tells us an associated belief state. There are still tons of possible worlds that we could be in. Where is the wumpus? We don't know, but the wumpus could be in any unvisited cell that doesn't have a stench next to it. But there are so many possible worlds that do adhere to these associated belief state, but this could be kind of this is what we know so far, and as we get new information, we can propagate that through the system to better understand and reduce the size of that belief state, with the goal of eventually reducing it to the point where you find the goal as fast as possible, I guess, is the goal. So this represents all states. At time 1, where the wumpus is alive, the agent's at 2-1, that square is breezy, and there's a pit either at 3-1, 2-2, or at both. And lots of possible worlds. This is a very common early state for the wumpus world. All that has to be true is the first action you decided to do, because you start in 1-1 facing right, is to move forward. Then one time step has elapsed, you're in 2-1, and all you have to do at that point is have experienced a breeze in 2-1. As soon as you have breeze in 2-1, you're in that situation. So very common to be here after a single step. But it represents every possible world where that sequence is what you saw in the first time step. So the goal from here would be to figure out which of those many worlds in that belief state you're actually in and be able to make an informed decision from there. It turns out from here, it's really easy to decide to explore 1-2. Because if you see a breeze in 2-1, that means 2-2 is not necessarily safe. That means 3-1 is not necessarily safe. That means we should go explore. Let's just draw this out so it's easier to see. So at time step 0, the agent was here. At time step 1, the agent is here, and we felt a breeze. So that means there's either a pit here or a pit here. So we know that it's silly to go explore here, we might die. Silly to explore here, we might die. We didn't see a breeze here, so it makes sense to go explore that. And this cell will tell us a lot about whether this cell is safe. Potentially this cell is safe, verifying that there is in fact a pit here if there is no breeze there. So that can tell us a lot just from that situation. And if we incorporate all of that, all we need is this knowledge to be able to do it. It doesn't matter which of these many belief states, many worlds in this belief state we're actually in. We can just still decide on something intelligent with minimal information. Questions on that? Right. The biggest issue with this is if we have some number of fluent symbols, then the possible belief states scale to an exponential number of states. So that's lovely. Sometimes there's information that you can decide and you can make an intelligent decision based on just that little bit of information. But if the goal is to reduce the size of that belief space, then that's going to be a challenge when there's so little information. So because of this, we have to oftentimes in the real world approximate state estimation so that we don't have an exponential size problem to reduce down. How do we do that? One way to do it is instead of having belief states as just kind of this black box, you represent them as a conjunction of literals. Time out to make sure that we know what some of these terms mean. A conjunction, do we know what a conjunction is from discrete? Or remember what a conjunction is?
Where things meet at some point.
Sure. That is a definition of conjunction, not the one from discrete, but it should be.
Yeah, like the elements from like multiple sets that are contained in both. Or
Yeah, it's a bunch of statements and it together. A conjunction is just a bunch of ands. A disjunction is a bunch of ors. So these are going to be defined with conjunctive normal form. That helps that everything is it's by itself. It's not itself an expression. So something like pit in 1-1. That itself is a 1 CNF literal. But if you had pit in 2-1 or pit in 1-2, that is now not 1 CNF anymore because it's a conjunction where each element of it is a disjunction. So you have ors as the objects that are anded together. So we can have at most one symbol in that literal. And that way it's just A and B and C and D, not A or B and C or D and et cetera. That would be 2 CNF. As we parse this conjunction of provable literals, then we end up with a new belief state, and we can update it. The previous belief state is discarded, and this helps to parse that. The unfortunate reality of this is that we can lose information. It's great for memory because we don't have to keep track of a history of belief states to help us to be able to parse all of the possible belief states that we're in, because that can require exponential memory. But something like, if we were to know, and you can see that this is a conjunction because everything on the outside of this is anded together. And we can see that as soon as we don't have things in 1 CNF, we can lose some elements of this. Like Wumpus is alive at time step 1, and we're in location 2-1, and there is a breeze in location 2-1. And the fact that there is a breeze tells us there's either a pit in 3-1 or 2-2. As soon as we discard that belief state in favor of a new belief state, we will lose access to the pit in 3-1 or pit in 2-2 because we can't prove one or the other. So we call this conservative estimation. Common problem across lots of AI. It's unfortunate, but it's a lot of the reason why we don't use propositional logic at scale. If there's any takeaway from like the last 10 slides, it's that recognizing and using a domain in propositional logic is a huge pain. That's kind of the big summary of everything we've talked about so far. Seems great, right? So we're going to transition and say, how can we actually utilize first order logic to make this problem a little bit easier? It's going to harken back to some of this material that we've talked about, but now we actually allow for variabilizing, and that makes our life so much easier. So now we can tell first order statements. That second one should be an ask. Program tell assertions and ask queries to use first order statements. My bad. So this probably takes you back to either discrete, or if not, then maybe you're seeing some of these things for the first time. But have we seen things like predicate logic statements of King John as a way of stating a fact, using a method that can return true or false depending on the value of the parameter? This is very useful if you're thinking in terms of object-oriented programming, where we could pass it an object and then analyze the state of that object to be able to determine, all right, is John actually a king? And this factors into predicate logic because based on certain logic, we can deduce elements or facts based on elements of first order inference. And we'll go over some ways to do first order inference here in a second. But so you can make tells that are just statements like John is a king, Richard is a person. For all kings, they are people. All kings are people. Are we familiar with the predicate logic for all and there exists notation? Remember that from somewhere, or looked at it because on the second slide of the first day, I asked people to review this. So this just says for all X, if X is a king, then X is a person. Shorthand, all kings are people. And this is how that would be methodized and brought under a quantification. Similarly, we can ask the knowledge base and say, can you prove that John is a king? Can you prove that there is a person? There exists some object in the knowledge base that is a person. You can also ask vars, as we talked about, like, is there a variable such that that variable is a person? So ask vars returns a collection of variables that meet the criteria. So this would return all variables such that person of X is true for that X. So ask vars is great for just getting back whatever it is that your query is, all variables that meet that associated criteria. We call that a substitution or a binding list, either one of those will work. And generally only used if the knowledge base only has horn clauses in it. I won't go too much into horn clauses because that's a discrete thing. But giving you an example, let's say in our knowledge base, we have something that says either John is a king or Richard is a king. We can see that there is no way to show that there exists an X such that that X is a king, because we can't prove for a particular element of the knowledge base, for a particular variable, that that variable is a king. We know there should exist a king, but we can't return the binding for which this is the king. This is the identification of that king. So from this clause, we know there is at least one king, but we can't state Richard is a king or John is a king. So we can't return a binding for this. So we have to be a little careful in terms of the kinds of asks that we make, because it can't logically make that inference and return a bound list. And it will try to do that. Questions on why that works the way it does? All right, well, let's apply it to the Wumpus world and make our lives a little bit harder. At each time step, Wumpus receives a first step list, that same 5 tuple that we've been talking about. So at time t, we're going to receive this 5 tuple, or a list of 5 elements, however it is that you want to think of it. It's really a 2 tuple, of which the first element is a 5 element tuple and the second element is the time step. So tuple inside a tuple. Any action that we could take in this world is a function. So like forward is a function. Shoot is a function. Grab is a function. Turn is a function. So we can now state and make claims about what this agent can do with respect to the functions that are the actions that that agent can take. And that's just the first order logic way of representing actions. We can then query what happens when we do something like an ask vars for a best action when we pass it a list of actions that could meet some criteria and we pass it the time step 5. It could then utilize that to attempt to return all actions that meet the associated some criteria of some kind. We have to define what that criteria is. So we could say something like return all actions, the best action such that the best action is grab. If it returns that at time step 5, that tells you you should grab. That is the best action available at this time step. Here are some examples of other criteria. So for all time steps and stenches and glitters and Wumpus, and I guess what's the rest of it? Yeah, climb is the last for everything that's aside from the breeze. So we had stench, glitter, There should be a bump in there somewhere. I guess the W stands for the bump, and then the climb. Then the percept at that, given that we're at time step T, implies that there is we feel a breeze. Regardless, it's saying it doesn't matter what any of the other percepts are telling you. It doesn't matter if you experienced a bump. That is irrespective of if you feel a breeze. If you get the breeze percept, then we can make the associated, we felt a breeze at this time step. None of the other percepts matter for that, which is why we can put them under a for all, as well as a for all time steps. So we no longer need something separate for time step 1, time step 2, time step 3. We can say, regardless of what time it is, if we experience a breeze, then we experienced a breeze at that time step, which seems really straightforward, but something that we need to be able to state. We can define something called reflex behavior. If we're able to, just based on the state, determine what to do, then that's great. It's kind of like whenever your reflexes are enough, you touch an oven, it doesn't matter what you're thinking when you do it, you can't force your hand to stay there unless you put something on it. Touch a burner, sorry, not an oven, but touch a hot burner, you cannot force your hand to stay there. It's a reflex action that you're going to take that regardless of the rest of the state of the world. That's just something that's built into you as a method of survival instinct. So it's kind of similar to this, you're programming survival instincts. Whenever we see a breeze, we label that breeze. Whenever we see a glitter, the best action is always to grab. We don't have to consider anything else. We can just program that as a reflex action. Nothing else matters. So best action, it's a complete function or has a defined behavior. We don't want to return nothing when we query what is the best action to take in this particular, if we haven't done the work to be able to return something, regardless of a state of the world, then we have what is not a complete or total function. Which means that there is a state where the agent doesn't know what to do, which means that we haven't done our job. Whenever you're creating a system like this, you want to make sure that whatever your best action function is, always returns something that is a total function. There shouldn't be any state that your system can be in where it can no longer return an action to you. It could be that you don't have enough information though, and it can return an unknown. It's okay to return an unknown, but it should still return something to you. So representing the environment question. What if we have glitter and breeze in the same cell? That's fine, pick up the gold. The breeze just says that there's something adjacent to us that is a pit. Because remember, glitter is only on the cell that the gold is in. If glitter said that it's adjacent, then we would have a much harder problem. But glitter, we only receive that percept if we're literally on top of the gold. And breeze is for if there is an adjacent pit. So we know danger before we step into it. We don't know the goal before we're literally on top. All right, representing the environment. The environment has objects. Yay, back to object orientation. So we could create an object for each cell, like each location. Any issues that we would have for that? The issue with that is defining adjacency. If we wanted to do something like say, all right, now we receive a breeze in a particular cell. If there's an object for every cell, then we have to define what that adjacency means for each of those cells. Adjacency in 2, 2 means 2, 3, and 3, 2, and 1, 2, and 2, 1. And every single cell would have to have adjacency defined for it. Rather than do that, if we define the object by a cell, a row column pair, then we can start to abstract the row and column of that and say, now adjacency can be defined by querying this method within a particular cell that has a row and a column field. So adjacency can now just be defined as for all x coordinates, y coordinates, a coordinates, and b coordinates, then we can define a tuple x, y is adjacent to AB. These are two different cell locations. If and only if expression. So we can now factor that out and make an expression that defines if this expression holds, then these two cells are adjacent to each other. If not, then they are not. And now we can quantify without too much effort whether two cells are adjacent to each other. And this kind of logic works very well in a predicate logic system because we often just care about, we don't need to return the list of adjacent cells to something. We just query, are these two cells adjacent? And now this adjacent function can tell us, yes, they are, or no, they are not. Which is useful. How do we represent pits? It's silly to try to identify them independently because there isn't really we never care to distinguish between those pits, I guess, if that makes sense. So instead, we can use a method to determine true or false, is there a pit in that location? It can also be unknown if we haven't yet proven whether there's a pit there or a lack of a pit there. So it returns just a ternary yes, no, maybe.
So for unknown, would that be like null?
It would be a separate thing. So we'd either return like true, false, or U, TF or U. And U just means that there is some probability between 0 and 1 that there is a pit there, exclusive. So you can start to imagine now as a logical agent, it's almost human understandable or human interactable. Where if I gave you these tasks of things that you can ask, you could start to make an informed decision just interacting with these functions. So an agent location, you can use a function called at that returns, you pass it the agent, the location, and the time, and that will return true or false, the agent was in that location at that time. So that will tell you where the agent is. You wouldn't care to use any time other than the current time step with regards to the process, but now you can take all possible time steps and condense them into a single method call. Similarly, we can make a Wumpus location that uses that exact same function. So note that there's nothing really different about querying the agent's location and the Wumpus's location, except the agent can move and the Wumpus can't. But from the perspective of the at function, it doesn't matter. It'll still return true or false. It takes the same three parameters, so we just combine them into one function. We can query whether any entity is at a particular location at a particular time. We can attempt to bind the location of the Wumpus once we know where the Wumpus is, saying that once we know where it is, it can't change location. So for all time steps, once we now have that location of the Wumpus is at 1, 3, then it doesn't matter what time step we're at. We could add this to the knowledge base, and we never need any further updates. From this, we can determine the location of the Wumpus. If we didn't have that information yet, this return would be unknown. We need rules that state that objects can only be in one place at one time. So you could assert something like this. So for all, let's see, cell at time step t, for all 1 and 2, for all possible objects 1 and 2, if S1 and S2 are at the same location at the same time, then they must be the same object. So basically it says if we can resolve both at x is both, or S1 is at x at time t and S2 is at x at time t, it implies that they're the same object. That's the easy way to do that. So yeah, it's two separate locations at the same time. So if this same object is at two different locations, it implies that it's the same location. It's like saying. We just instantiate the object, I think it makes sense. So if I say some random person in here is, if they're in location 1 or they're in location 2, because we can't be in 2 locations at once, those 2 location objects have to be the same or refer to the same thing. That could be this classroom. Because we can't be in 2 places at once, I can't be here and next door at the same time. So if I am in 2 locations referring to 2 different objects, those 2 objects have to be copies of each other. Kind of the logical way of stating that. Does that make sense? We find this all the time in predicate logic, these kinds of implications of ways of saying only one. If there would be 2, then they must be the same thing. That comes across all the time. How we doing? Time to take a break, probably. Been about an hour. All right, let's take a quick break. We'll come back in a few minutes.
Okay, bro, but you don't anymore, you're not cool anymore.
Exactly.
Cigarettes, wait.
Yeah, if you wanna be cool, smoke a pack of cigarettes right now.
Yeah, prove it, Daniel.
And that is the first thing on the coming back from the recording.
You got.
That's the first thing that you hear.
I saw that. It's like the sins, bro.
Yeah, I know. The TV.
All right. First order logic, way less fun than this discussion, unfortunately.
We could just stay in happy place and not come back to this.
You want to learn about for all X, Y, A, B adjacent, X,
We
Y.
could just pretend we did. We'd all be happier for it.
Right, for once.
Yeah.
All right, continuing on, drawing conclusions about the world from agent percepts. So as we gather data from the world around us, what can we figure out about the world when we get that information of a bump or an update? So we could say something like, for all S and T, if the agent is at state S at time T and there is a breeze at time T, it implies this new function breezy of S, where that state is breezy. We don't need any associated time parameter. Note that the conclusion we're drawing has nothing to do with time. Because once a state has a breeze associated with it, that never goes away. So we could now differentiate between a breeze of the percept and breezy, the state of a location in the world. We can then assert logic for determining the location of pits by saying things like, for all states, if S is breezy, then it bidirectionally implies that there exists some R that if R is adjacent to S, that R is adjacent to S and there is a pit at that location R. It just says that there exists a pit. Anywhere there is a breeze, there is a pit adjacent to it. We can use this in combination to figure out the location. Once we can prove that there is a pit in a location, this will help us to do it. Maybe we can try to draw an example of where this might be useful. So where's an instance where we might be able to make an assumption about the location of, speaking of, luckily this is just not a mosquito. Otherwise I'd send it Sam's way. So we feel a breeze here. This place is visited and safe. This place is visited and safe, and we haven't been here. And this place, let's make it out here. This place is unknown, this place is visited and safe. So we know there must be an adjacent cell to this breezy cell that has a pit. If we have visited and all of these locations are safe, then we can determine that there exists some location that's adjacent to it and has a pit. If we query ask vars for all adjacent cells to this, it would return this cell, this cell, this cell, and this cell. We can then show that this cell does not have a pit. this cell doesn't have a pit, this cell doesn't have a pit, so the exists some location that's adjacent and has a pit must be referring to this location. So we can replace the question mark with, there's a pit here. And we can logically determine that via some of the processes that we will go into when we talk about first order logic. And how to actually make those claims. So once we can prove something, then we can iterate on it and get that result. Note that we don't need a long list of axioms like we did in propositional logic. Those axioms were really tedious and annoying. All we need is this one statement, because it's kind of, it works by associated definitions. And those definitions are general definitions because they've been, what's the best word here? Variabilized in terms of this concept of adjacent that works for all cells, rather than having to state adjacency for every single cell. So that you look up, all right, I'm in 3.1, I have to look up in the adjacency table for this particular cell. We can state, because of that general adjacency and the fact that any cell that is breezy has to have an adjacent pit. An adjacent cell that has a pit. And likewise, if we see that some cell is adjacent and we know it has a pit, then we can tell that every cell that is adjacent to it is breezy. So if we can identify the location of the pit, we start to know things about locations that are around it, even if we haven't visited those locations. So people know that I'm using bidirectional implication or elimination when I do that, right? Is that apparent? Who remembers, or is, I guess the better question is, who's fuzzy on bidirectional implication and what that means? Okay, it just means that this is the equivalent of saying we have an implication in this direction and we have an implication in this direction. So you can break this down into two statements. If this is true, then this is true. If this is true, then this is true. So that's the bidirectional implication. And says that if we can show one side or the other, then we can infer the other side from it. Man, discrete sucks, Jim. Sometimes.
I also took it 5 years ago.
Right, oh yeah.
So like,
Totally understandable.
it's been a minute.
Totally understandable.
It's also when I decided, like, pre-deciding I wanted to be an okay student. So, you know.
That's fair too.
I was there to get the C+ and roll out.
Oh, yeah.
It's like me at all you can eat restaurants. I'm just here so I can be rolled out eventually.
That was a good one, it took me a second.
I like the jokes that take just a second. All right, so now we can quantify over time as well. So we can state something like, just like we did in the propositional world, if we have the arrow at time t+1, it bidirectionally implies, and again, just means implication in both directions, if then rules in both directions. If we have the arrow at time t+1, that means we had the arrow at time t and we didn't shoot at time t. If we have the arrow at t and didn't shoot, then we have to have the arrow at time t+1. Both of those work in terms of the cause and effect. I like to think of implications as if then, cause and effect, however you want to attach yourself to it. But that's just all that means. But it works really nicely because we can just quantify over t for all t. We don't have to give a list for every possible time step like we did in propositional logic. We can say, as long as we're at a legal time step that t could quantify over and b, is the 10th step a legal time step? Yes, it is. So at time 10, if we have the arrow and didn't shoot, then we know we have the arrow at time 11. We don't need to state that for every possible time. We can just quantify over it. All right, what I really should have done before displaying project rate, probably push this a little bit later. But I'll at least introduce it. I'll try to get this up. I don't anticipate making this due for at the very least a week. My best guess is this is going to be either late next week or possibly even the start of the following week after that. So this is going to be a longer term project. People should have a long time to work on.
Maybe AWS goes down.
Then we'll extend it more and I'll start to yell at Amazon and demand that they personally ship me their entire inventory. I can't store that. What should I do?
Build another warehouse.
You could use the basement of this place as a warehouse.
That's true. There is a good bit of storage around here, and that way I could give just the students I like access to it. All right, so first thing you're gonna do is learn about the natural language toolkit library that exists. So I think I've asked this of random people as you come to my office, but who has heard of the programming language Prolog? One person, excellent. It is a logic programming language that exists solely to emulate logic like we've been describing it. So you can ask and tell, it will use all of the associated logical inference procedures that we are about to describe to be able to return to you valid information that can be logically derived. And of course, Python has a library that allows you to emulate basically everything that Prolog can do. So this is Python's way of being able to set up and incorporate logic and allow you to take a logical approach to a problem like this. So you will make an agent that intelligently solves the Wumpus world. If you do a good job at this, it will never fail. So the goal is to make it as robust as possible. So that's part one. You want to make sure that it's trying to maximize its associated utility. So it's going to have the same reward structure when it escapes with the gold, plus 1,000 points. When it falls into a pit or gets eaten by the Wumpus, minus 1,000 points. And for every other action it takes, it's -1, I guess, except for shoot, which was -10. So the goal will be to represent this problem logically. And of course, you can refer to these slides to set that up as you would like, but try to think about making this as simple and as efficient as you can. Part two of this is, of course, just like in project one, you're going to receive someone else's solver for the Wumpus world. Now, just one instead of 3. And your task when you receive someone else's solver is, of course, try to break it. And the way you're going to do it is you will be able to manually create your worlds. So you'll be able to place your pits, place your goal, and your task is to identify, to look at their solution and try to create a world that it does not perform well on, or that it's just not prepared for in some way, shape, or form. This may be impossible if you make it perfectly robust, but it is intentionally going to be a challenge for it to be perfectly robust. But the closer you make it to robust, the harder you're making the life of the person who gets your program in part 2 to try to find some way to have it break or die or something that gets a very bad score. Then you're going to figure out what changes could you make to their program. Just again, a singular small change, kind of like you did in project 1. A single small change that will cause that agent to perform poorly. And again, bonus points to people who can do something that would evade a common unit test that you might think, anything that would be undetectable. And then run their program with that change and see how much damage you can do with a single small change. What would you attack? Where would you go make that associated change so that it stops performing the way that it should? Part 3, you'll get your original solver back. However, the anonymous change will have been made to your program. You are not allowed to just run a diff on your original submission.
Damn it. I was like, cool, part 3's in the.
Yes. So I want you, without your original solver at all, just seeing what you can do with this is to attempt to find that change. You can look at the code, you can run the program, and basically you're going to time yourself from, and there's no part of this grade that has anything to do with this time. This is just for data and for information. Time yourself from when you start this process to when you identify what was changed and how it was changed.
We like
So
pause it if we're like not actively working on it? Or do we like just have to?
I want it to be a one shot. try to figure it out, so carve out at least enough time for you to really hone in on, look at the code, if it's not apparent, look at the behavior, if it's not apparent, try to figure out what was changed. So note that you can design part 2 around knowing that part 3 is coming for them. So now you want to make the change, it's going to be as difficult as possible for them to find and identify what was changed in their
So
program.
this is, like, diff makes it way too easy for sure.
Yes.
But isn't that like realistic? Don't you check? if
Yes.
Stuff hasn't been changed.
You absolutely would check if things haven't been changed. But the idea is to train your critical thinking and code analysis skills to be able to take in and say, all right, something's not right here. Maybe a diff didn't catch it. Maybe something was modified in a way that still returns that it's working correctly. But you know it's not quite behaving. There's something that tells you it's not behaving the way that it should. And there's no easy just diff to run on that system. So being able to, I wanted to create kind of a black box, a test box for you to go in and try to identify what is and why isn't this working the way that is expected.
Okay.
Yes, there's an easy solution to this, but the alternative is to create a real world sized problem that, and I don't want to quite set that up, and I don't think you want to interface with something that's quite that large. So I wanted to reduce it to the smallest possible problem and then just say, this thing that would easily trivialize it, don't use it. So don't use a diff for part 3. Then I want you to write up what happened. So in software engineering, it's called a postmortem, but think back on your performance for yourself in part 3. Do you feel like you could have found the issue faster if you had done something differently? What would you have done differently, either in terms of part 1 designing it in the first place to make it harder to make that associated change that was difficult to identify? In part 2, did someone just make it so easy that it trivialized your own finding of it? Were you happy with how fast you found the change and felt like that was, are you proud of it? That can be the answer, and I'm pretty proud. I don't think I could have done this much faster with the knowledge of what actually happened from the result of that. That's totally fine. But I'm just curious to see your critical thinking on an analysis of
I
what
want
happened.
to know who did mine.
Yeah, I think it'll be fun to talk about. I think it's gonna be really interesting to talk about.
To send them pictures of their family.
You disturb me, Thomas.
You haven't even got my package yet.
What does that mean?
Based on what I just said.
Oh, great.
So again, I have not officially written this up yet, but the grading for this will only be based on the quality of your solver. So how much of part 1, how robust did you make this? And then the quality of your analysis. Again, not factoring in at all the time factor.
This is like a 2 or 3 week assignment, or are we doing?
Yeah, something probably closer to 2 weeks.
2.
But I anticipate that part 1 is going to be a very long and involved process. So part 1 by itself is probably close to 2 weeks. And then there'll be a week after that to kind of write up and think about. But yeah, making this logical agent is not going to be easy. There will be a lot of considerations, a lot of research that goes into doing that.
So for part 2, I imagine that he wants to also run their code, right? So
Yes.
if for part 1, should we also provide documentation? Documentation.
If it's not apparent or obvious, I am imagining that what you're producing in part 1 would be close to production level code, and that way part 2 is an analysis of production level code that you would see if you hacked into some system and were actually modifying code. And I am very curious how this goes. So keep in touch with me as you develop this. I will be, again, first time I'm teaching things, I'm very curious how this process works. What's a struggle, what's not a struggle, what you find to be easy, more challenging than you thought it was going to be. So just getting that on the schedule, yeah.
I think you may have said this already, do you keep a map of what you know? Do you take it along with you as a history, or do you have to imply your history from your?
It depends on how you set it up. So there are ways where you store elements of that history and that becomes part of your knowledge. In a predicate logic database, you're gonna end up with lots of just facts.
Yeah.
And so as you derive new facts, you add them back into the knowledge base, and that can be used to determine new facts, based on the associated either forward chaining, backward chaining, resolution. We'll talk about all three of those as a way of doing predicate inference. So you're not quite ready to do this yet because we haven't talked about that. That said, this library will do a lot of that for you. So you only have to worry about what is the initial knowledge base. How do I represent the initial knowledge? Because you will be able to query just inference. But it's useful to know exactly how that inference is done so that you can have a sense from a design perspective of what that initial information needs to be. So there's still a bit to go before I feel like people can start on it, but I did originally put this here because now you can at least start looking into this library.
It's pretty weird, because it's using like what you would assume are escape characters,
Yeah,
but it's not, it's logic.
it is logic.
It's just how they are doing linear algebra. Or,
Predicate logic.
yes.
Yeah, so I think this is gonna, my hope, I guess, I shouldn't say I hope this is going to be a lot of fun, because I can imagine that I would be having a lot of fun interfacing with other people's code, trying to break it, trying to produce code that is as difficult as possible. So part 3 is going to be as difficult as part 1 was easy or hard. You half-ass part 1, part 3 is gonna be really hard. You do a very good job on part 1, then part 3 is going to be easier. That's gonna be interesting to see just how, from my perspective, how that goes. Any other questions about this before I fully write it up and give a full grading rubric and a bit more on exactly what I am looking for in terms of these associated write-ups? Initial thoughts without having done any of the work yet? How do we feel about it?
It's kind of a hill with how this library.
Yeah, there's a lot to learn with it. So I do think part 1 is going to be the most challenging, and I think there's gonna be a lot of, don't procrastinate this until the last minute, because it's gonna take a while to learn the library. It's not typical programming. It's not programming like you might be used to in an object-oriented environment. It is a different paradigm completely. And we don't really have a programming languages course. So you haven't necessarily, unless you've been doing this on your own, been exposed to different programming paradigms. How this works is very different from how any object-oriented language works.
Just type, so it works. It's the same thing.
Other questions, other thoughts about this? Right, we will move onwards. Given that you have a problem that is solvable with first order logic, how do you engineer a solution? What process should you go through as you think through it? How do I engineer this from its associated components? I want to give you a general process, and step by step, think about these steps, and that will help you to construct an initial knowledge base. So first step is just to identify the questions. What is the knowledge base trying to do in the first place? What would you want to be able to ask the knowledge base? What do you want it to return to you when you ask it something? What does it need to know to be able to respond to those kinds of questions? Given that we're in a current problem state, what information is available for query? that helps you to design the associated system. Does the knowledge base itself choose the actions? Or does it only need to answer questions about the environment? So that's a big differentiator in the engineering of a knowledge base. Is it returning an action, or is it returning yes or no only? Or a result of where should I go from here? Part two, what's the relevant knowledge? What are the boundaries of what belongs in the knowledge base and what is outside of the scope of the knowledge base? As an example, I chose designing security for some other company. You would need to ask them as a client, what are the requirements and specifications for their needs? Then you translate that down into the technical needs that you are going to implement. I'm making some assumptions about your role in this, but as a software designer, those are the kinds of questions that you would need to be able to ask. And designing this knowledge base is very similar to the process that you would go through when making a requirements and specifications document. Except there's no client, the client is the domain, the client is the problem in this case. So ask the Wumpus World client, and the rules of the Wumpus World will be your answer, but this is just kind of in general. We need to then focus in on a vocabulary. All of the associated predicates, that's going to be the names of your functions, the names of your variables, the names of your constants. We go from analyzing kind of the rules of the Wumpus world down into, all right, now we know what breeze represents. We know what location represents and what it takes in terms of its parameters. Question?
A minimum grid size for, what was it, 4x4, or is it?
What I want to be able to do is specify in general a larger world. So a 4x4 world is such a toy size that it's hard to, it's easy to engineer a solution. It's hard to create edge cases in a 4x4 world. So I think when I do assign this, we're going to bump up the size of the world to be able to create some fun. So maybe something like a 10x10 world, or I don't think you gain anything past a 10x10 world. You should be able to create all of the associated edge cases you would ever want to, I think, in a 10x10 world. This isn't going to be the same as Project One, where I expect some kind of scalability to a 100,000 by 100,000 world or anything crazy like that. I want the focus to be on the logic itself and not necessarily the scalability. So I'll finalize that decision, but anticipate something like a 10x10. We have domain level concepts. So these are like, if I were describing the rules of the Wumpus world to you, those are domain level concepts. You're going to turn those into logic level names. So what are the associated, and when you come up with that, predicates, functions, and constants, tie that. It doesn't necessarily have to be the same as the Wumpus world's definitions names, but you can start to name things and ideas in ways that logically work for you. Very similar to programming style in that idea. You end up with an ontology of the domain. Useful. Step 4. How do we encode general knowledge about the domain? So now we need the ability to write axioms for the vocabulary terms. How are they related to each other? How can we factor out some of the complexity of this in terms of the associated functional representation of the domain? What do the associated terms mean? Are there gaps in the vocabulary or gaps in the knowledge? And as you start to play around with your own program, you will find that there are times when it returns an error or just accepts out of the program because it isn't able to return, or it spins forever in the knowledge base, proving new things, but none of those new things help you to identify what the next action should be. So noting what those are and then finding out, okay, why? Why is it spinning forever on this? What is it missing logically? In order to be able to make a decision about what it needs to do. If you find some issues from this, then you just return back to step 3 and remake your predicates, constants, and variables. And now you have an expanded domain that hopefully handles more of the necessary embedded logic. Then we can make a description of the problem instance. Now we can start to actually test things. You will start to write atomic sentences, something that says things like, we start in cell 1, 1. The location at the beginning in time step 0 is 1, 1. And then you can just kind of set it free, make a world for it, and see if it's capable of doing what it's supposed to. If you log well, you can analyze the log of what it's doing or how it is determining what to do next, and that can help you to find the associated gaps in the logic. We know everything comes from the percepts of the agent, so if you're able to record that associated data, then you can more easily find bugs. It's very similar to just getting data from log files. It's just how you determine what state you are in. Finally, queries to the inference procedure. That's embarrassing. Queries to the inference procedure in order to get associated answers. So at the end of this, you should be able to feed it an arbitrary world and have it perform intelligently at the end of that. You gotta tell me what's on your mind, David.
Look, the one booth.
Okay, that may be acting intelligently. Whoever gets David's program, don't take it too seriously.
There's gonna be like 7 walruses.
No, I'm just saying, I'm assuming that the action shoot just does something completely different in David's program, and it is exactly what you just said.
Oh, no.
David's NSFW. David's NSFW. Whoa.
Not safe for Wampus. All right. Once you actually have something online, then yeah, debug and evaluate. Does it do what it's supposed to do? You can determine from there any missing axioms. You can determine things like something that's difficult to find. If smelly is a particular state, has a stench associated with it. Remember, stench is a percept. So a location might have the smelly associated with it. Then we know that something adjacent, the S adjacent to the lumpus, this state is adjacent to the lumpus. There we go. I don't know what home represented there. What was I on when I wrote this?
Something that we don't have access to.
There's something that I need to go back and review before I know exactly what that means. Then we can also determine things like the incorrect logic. So what happens when you see the glitter and suddenly your agent wants to run to the nearest pit and jump in it? So there will be times when the associated logic that you've written returns an action that intuitively is not an intelligent action. It's not what the agent should be doing. So you will then debug that and figure out why is it logically determining to do that. It's using correct logic. It's just a matter of what is it doing to determine that that is the right action to take in this situation. As an example, if you say something like, for all x, if x has 4 legs, then x is a mammal. There are certainly 4-legged creatures that are not mammals. So maybe you have made an incorrect tag for something somehow by using some kind of, this is a perfectly legal predicate logic statement. It works, it's predicate logic, but it doesn't necessarily represent the rules of the domain. So if you write incorrect logic, then your agent will start doing some pretty strange things. Or concluding some strange things about the world. And maybe that becomes something, as it takes that into consideration, it then chooses the wrong action or does something you would not expect. So just like in programming, your unit tests will become more like unit queries in this case. So you'll be writing test cases for your own program saying, all right, starting here, all right, you'll create some test cases for yourself and maybe even some test worlds where you know where the gold is, you know that the gold is possible, you should be able to see from this world, here is exactly the sequence of steps that my agent should be taking in order to do the thing. Start with 4x4 worlds or even smaller 3x3 worlds, and you can handcraft small worlds to ensure that your program is working on these smaller worlds to get the basic functionality, and then blow up the size of the world once you know that it works for 3x3 or 4x4 worlds, blow it up to a 10x10 and see if it still works and what breaks. A lot fewer things will break, and it will be a lot easier to debug if you're in a test size and you make some test instances. So just like we would have unit tests and integration tests, you would have unit queries and integration queries as your different logical components come together. So you can think of this very much like a software engineering process. We've all taken a software engineering course, right? Hopefully at some point.
I would say I did.
He took it from me. That's a slight to my heart.
I'm kidding, it's my favorite class I've taken.
All right, so we went from a slight to utter bullshit. I love it.
It's the only one I've taken from you, so, you know. I guess this one now, but it's.
You're calling this not a class.
Yeah, come on.
All right. So how is inference actually done in first order logic? And in the case of importing a library and using this, for the most part, you should not have to program this, but it's something that I think is important to know how it is done so that you can look at why something isn't working that should be working. So if you understand first order inference, you should be better at debugging what's going wrong in the associated logic. If it's using resolution and you go try to apply the resolution manually yourself, then you should see some kind of where the process goes wrong. If it's supposed to be able to resolve something and it doesn't, then what about that process? Where did it go wrong in that process? What about my representation of the world didn't allow for this process to succeed? So this goes kind of from the using the tool to understanding the tool. So I'm hoping that's what we can get with regards to inference. And thankfully, from here, this becomes a little bit less abstract and we can apply this to some actual problems and utilize inference on some toy problems to see how you can generate new knowledge. So how do we take information from a knowledge base and derive new facts from it? This is what we as humans do all the time. Our percepts are our senses. As we gather new information, we take our cumulative experience up till today, plus the information that we gather from our senses from today and learn new things about the world around us, how we work, the rules of the world. And then you incorporate that into your knowledge base, and then you go to sleep and wake up tomorrow and do it all over again. So we need a process, a logical process to do that. So first we need to convert first order logic down into propositional logic so that we can reason over propositional logic. The entire purpose of predicate logic is that it's easier to program in, but we need some way to make sure that we can operate logically on that. It is not easy to operate logically on predicate logic, and it's actually much easier to operate logically on propositional logic. So this is where the ties from the first part of this and the second part of this come together. It's like a, why don't we program in assembly? We program in some other language and convert it down to assembly because no computer can run high-level code, nor should it try to. Unnecessarily complicated, but there's a middle procedure for how we write the code and how the CPU runs the code. Let's give you an example of inferring sentences obtained by substituting a term without variables. So here we have a statement for all x, whatever objects x can possibly be. If x is a king and z is greedy, that's x, that's an x as well, I just can't see. If x is a king and x is greedy, then x is evil. Now we can use some kind of instantiation somehow to be able to go down to and say, all right, well, we need to substitute x for John. If we know that John is a king and John is greedy, then we can imply that John is evil. We need some way of making that connection from an arbitrary variable to an instantiation of that variable. X is just an unknown. John is an instantiation of that variable. So we know if Richard is a king and Richard is greedy, then Richard is evil. We can go a step out and say if John's father is a king and John's father is greedy, then John's father is evil. And now we have some, I guess I want to call that recursion. Functions inside of functions. In general, if we have, this is called universal instantiation. If we have some universally quantified statement, then we can substitute some variable for which that adheres to the associated constraints of that variable. So for all x doesn't have any constraint on it. Anything that could be substituted for x can be substituted into king and greedy if both of those return true. Then we can derive that x, whatever x happens to be, is also evil. So this is called universal instantiation. Taking a general idea, taking some possible substitution for that, and then making a conclusion on the instantiation of that object. Going from the general to the specific. So alpha here is just the sentence. B is the variable, G is what we're going to call a ground term. That allows us to go from determining that X is evil to determining that John is evil, or Richard is evil, or John's father is evil. We can eliminate its existential quantifiers with existential instantiation. Existential instantiation just says, so if we have an existentially quantified variable, there exists a student in this class who is bored. So it doesn't tell us anything about which student is bored, but I can create kind of an outline of a student on the board as like I know this is one of you. I don't know which one it is, but there is now this, we can carry forward this concept of this student which is bored. So here's another example. There exists an X such that X is a crown and X is on John's head. We can now existentially instantiate this with a new variable's name. All right, there exists some object C1. We don't know what C1 is. We don't know where it is, but this object C1 is a crown and it is on John's head. And now whenever I refer to this object C1, I can query something like, is it a crown, which would return true. It's giving a name to something, even though we can't necessarily specify the exact object that it is yet. But I can start referring to, I know one of you is bored, so that student who is bored, stop looking at your computer and look up. Pay attention. And now I don't have to be using any name, but if it refers to you, now you know it's referring to you, and I'm not using your name. I guess that's kind of a similar analogy to this. And now I don't have to call you out. All right, so existential quantification, replaced as a single instantiation, great. Universal quantification can be replaced by all possible instantiations of that object. So if we said something like all students in this class are bored, then now it doesn't matter that I don't use your name, I can just go individually to every single student and say, you pay attention, you pay attention, you pay attention, and it will apply to everything that is universally quantified. So let's give you an example. Universal instantiation for the following. For all x, x is a king and x is greedy. If that is true, then x is evil. We know John is a king, John is greedy, and Richard and John are brothers. So how does universal instantiation work for this? We find that if John is a king and John is greedy, then John is evil. If Richard is a king and Richard is greedy, then Richard is evil. Everything that could possibly now, every object that could go into this is by universal instantiation. And note that some of these will return true, and some of these just don't do anything. What was something like, in order for this to be true, this has to be true. So if there's an aspect of this that's not true, we can't conclude this. Since both of these are true, we can conclude this. But this turns into two statements now that we can determine the truth value of based on the information that we have. And if we ever could derive new information that Richard is a king, somehow via some work, we derived that Richard is a king. And we derived that Richard is greedy. We now have, because of this universal instantiation, we now have the ability to derive that Richard is evil. Even though we don't currently have that information, the fact that we did that universal instantiation makes sure that if we can ever in the future prove that, then we can conclude that. Does that make sense? I think that also helps to justify why you would instantiate this with things that we cannot currently prove. Maybe in the future you can prove that as you derive new information. We can now replace sentences, things like John is a king, with propositional symbols, because we can't have functions in propositional logic, but we can have things like statements. John is king. That returns true or false, and that is fine in propositional logic. Location 1-1, that's true or false, depending on whether the agent is in location 1-1 at a particular time step. So they can return true or false. Of course, there could be an infinite possible number of substitutions. Let me give you an example of this. This is something that you should be aware of when you query. This is useful for your project coming up. If you can create an infinite sequence of statements. So father of John can now construct father of John, can construct father of John. So if you allow universal instantiation over father of something, then that becomes a new entity. You could say, all right, father of John gets something C1. What can I do with this? Well, I can take the father of that object, and we'll call that C2. I can take the father of that object and call it C3. This process will never terminate, and you will have objects that represent all possible people, that represent the entire male lineage of poor John. This will spin forever. And then we throw it in the first chapter of some new Bible verse or something, and we get some long, the father of 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 John is the father of the father of the father of the father of John, something like that. Famous theorem randomly from Herbrand. Any sentence that's entailed by a first order knowledge base, there's a proof involving some finite subset of that. Just means that, yeah, this is not terribly important at the moment, but I think it's important to, the takeaway from here is to ensure that you're not creating any predicates that can cycle forever when you go through the instantiation of that. At least without some way of terminating. It's like an infinite loop in programming. Infinite logical recursion. Stack Overflow. So that's instantiation. Let's talk about unification. We end up with a bunch of unnecessary instantiations when we go through this process. We're going to find that we have a bunch of objects that are completely and totally useless and or represent the same concept. So keeping instantiation efficient, we want to be able to determine if we have two sentences, can we unify those two sentences into one object? This is allowing us to substitute something for both such that they become identical. So something like, we want to know who John knows. So we would do this as a query to the knowledge base, ask vars knows John X, and that's going to return all X such that John knows X. Who does John know? That answers that query. And this would be unification. Every variable that unifies with X. For which variables can we substitute X for that variable such that this query is true? One thing that may be in the knowledge base is a random fact. John knows Jane. Jane would unify with X in this ask vars, and now we can determine that with a substitution of X for Jane, then knows John Jane and knows John X, where that substitution is X for Jane, those two different statements unify and represent the same information. So that means that it's a legal substitution. On the other hand, knows X Elizabeth is the exact opposite question. This is who knows Elizabeth, not who does Elizabeth know. So as soon as we put the X in the first place instead of the second place, now it's asking kind of the opposite question. If we unify it with knows X Elizabeth and everybody knows Elizabeth, then we end up with failure. Any ideas why this doesn't work? These are in tandem. So we knows John X and knows X Elizabeth at the same time. And yeah, there's no real way to know, but it's because X can't take on two different values at the same time. X has to refer to the same object. So because of this, we can't have X be substituted for both Elizabeth and John at the same time. So John would know Elizabeth because everybody knows Elizabeth. But here, X would be substituted for John, and here X would be substituted for Elizabeth. We can't unify X to be two different people since X needs to represent one entity and not both entities at the same time. Does that make sense? So this is a common mistake in predicate logic kinds of programs, because as soon as you flip where the variable is and call it the same thing, it will attempt to unify that variable. What are all of the variables that X can take? And you will find nothing. There is no X such that John knows X and X knows Elizabeth when there are only two people in there, John and Elizabeth, and they know each other. So even though it should return that John knows Elizabeth, it will return nothing. So common bug. Questions on that? Does that make sense?
I think a little bit of like SQL.
Yeah, it has SQL itself is actually very logical in nature. It's data driven, and there's a little bit of a difference between logical and data driven, but they're kind of related, I guess I would say. We can then talk about this concept of a most general unifier. And of course, the issue is that there can be multiple unifiers for a pair of sentences. Everything that could possibly unify with that. So as an example, knows John X and knows Y Z. If we query both of these, then we may find that Y can be John and X can be Z. We find a legal substitution where whatever X could be is what Z could be. Does that logically follow to people? It's making a substitution where instead of giving you an actual object, it gives you a variable. That becomes interesting. If that is one possible return, then it gives you the result that John knows Z, which is a little strange, but that is one of the things that ask vars could return from you or return to you. On the other hand, it could return that Y can be substituted with John, X can be substituted with John, and Z can be substituted with John. Why would that be a possible return? We do need a couple extra substitution rules in this, but this is something that, depending on how you set up your knowledge base, could actually occur. And if we do this, we would be able to conclude really strange things that John knows John. Maybe that's intended, maybe that's not, but depending on how you set up your knowledge base, you may find that to be a bug or a feature. If you give an additional substitution, Z for John, then that absolutely can be returned. So John knows X and Y knows John. So it makes sense that both X and Z, or sorry, X and Y are John, given that Z is John. And then we conclude from that that John knows John. So when we do this, the former is more general and the later is less general. The reason for this, fewer general restrictions on the variables. Here, we made one substitution. And here we made 3 substitutions to be able to conclude that. So we can utilize this concept of the most general unifier in a way of saying if there is ambiguity in terms of how to interpret the associated logic with the potential substitutions of maybe an extra substitution for Z and John, there are fewer constraints here than there are here. So maybe we should return this instead of that. You can set up your knowledge base to return either one, depending on how you work with it. But in general, that most general unifier unification result, placing the fewest restrictions on the variables. We'll actually see this in an image form fairly soon. Looking at this as an algorithm, we can just code it up. You'll explore 2 variables and build the unifier. If at any point the structure of it does not match, then it's not a unify. And we return failure. So we will attempt to unify everything with everything, at least given that we can pass in parameters that help to reduce that domain. But now that we have a partial query, what unifies that fits substitutions with everything that is left as a variable? And of course, if you try to match a variable against something that is more complex, it doesn't have a single variable inside of it. Maybe it has 6 or 7 variables inside of it. Now you have to look at every combination of values of all of those variables and try to, so it becomes exponential in scaling based on the length of the number of variables that are in that query. If that makes sense. It's like if I had to ask, who is friends with Robert? And the answer could be, now I iterate through all of you, that's fine. But now if there's an associated structure to that I have to look at every pair of students, every triple of students, you start having to look at different subsets of all of that, and that will start to scale as you have more and more unknowns in that. So we have to check if the variable is also inside of the complex term so that you have self-reference. as an example, we don't want to allow S of X to unify with S of X, because then we get a nice logical infinite loop. So if you force the user to do this, you get linear time. If you don't, you get quadratic time. Cool. How are we doing so far? Feel like 2.5 hours into a 2.5 hour class yet? We fading? Faded. It looks dead in here. Let's just stop here. I don't know if people are gonna get too much more out of it with the next slide, but it looks like I have successfully lulled you to sleep. Watch this lecture back as you go to sleep. It will help. Until I crack a really bad joke and then everyone laughs. Huh, what?
That's happened.
Well, yeah, so pick this back up.
Project plan.
Yeah.
Is that what you have in the slides?
Yes, so you have one of these.
For,
There's a-
yeah, for which, I can't really of that.
Yeah.
As I would like to have a more detailed result for that, and I currently don't have time for it, so it's a matter of, can we get data from that and see that?
What's like?
I wonder if the smallest like building.
So the question was, are we gonna have a more detailed? Results from kind of the results of parts.
Or something like that.
And I don't think that I can do that, so I suppose like the way that I have this square set up is slowly draining the life out of me. But
Yeah, like.
if you can find some data from that or find some data from that, that would be awesome, so that so kind of. Like this whole data. Yeah, across the whole class question.
I'm not telling you.
So you work with like.
I think I have 5.
Yeah.
Good ones too, yeah.
No. But if you do,
Oh.
wait, you get it there.
I was thinking, does that mean it's no more than
Whatever,
also you can naturally just about that.